Welcome everyone to today's presentation on deep learning with Keras and Tensorflow. We'll explore the fundamentals of machine learning and deep learning, delve into building models using Keras, and discuss strategies for evaluating and tuning these models. Let's get started. Tensorflow is an open source deep learning framework developed by Google, widely used for building and deploying machine learning models. Keras is a high-level API that runs on top of TensorFlow, simplifying the process of creating neural networks with its user-friendly interface. TensorFlow is an open-source deep learning framework developed by Google, widely used for building and deploying machine learning models. Keras is a high-level API that runs on top of TensorFlow, simplifying the process of creating neural networks with its user-friendly interface. To define a model, you add layers such as dense, convolutional, or dropout layers. After defining the architecture, you compile the model by specifying the loss function, optimizer, and metrics. In Keras, you can build models using either the sequential API or the functional API. The sequential API is straightforward for stacking layers linearly, while the functional API offers more flexibility for complex architectures. In this code, we import TensorFlow and Keras modules. Define a sequential model with 3 dense layers. Compile a model with the Atom optimizer and binary cross entropy loss. Print a summary of the model architecture. The output displays the TensorFlow model summary showing the architecture of the neural network, including the number of layers, their types, output shapes, and the number of trainable parameters totaling 300 to 1. It also includes informational logs about optimizations, warnings regarding input shape usage in sequential models, and CPU instruction support for TensorFlow computations. Evaluating your model is crucial to understand its performance and generalizability. Common evaluation metrics include accuracy, precision, recall, and F1 score, each providing different insights into the model's predictions. Model tuning involves optimizing hyperparameters such as learning rate, a number of layers, and number of neurons to enhance performance. Techniques like grid search, random search, and cross-validation are commonly used for hyperparameter tuning. This code builds a neural network using TensorFlow and Keras to classify breast cancer as malignant or benign based on the breast cancer dataset. The data is preprocessed by splitting it into training and validation sets, followed by scaling with standard scaler for normalization. The model has a sequential architecture with 2 hidden layers using RealU activation and a sigmoid output layer for binary classification, optimized using the Atom optimizer and evaluated with accuracy as a metric. This code trains and evaluates 2 neural network models to classify breast cancer data. The first model is trained for 50 epochs with a batch size of 32, and its validation accuracy is calculated and displayed. A tuned model with an updated architecture, increased neurons in hidden layers, is then defined, compiled, and evaluated similarly to compare the impact of the architectural changes on validation accuracy. The output will show the validation accuracy of the initial model and the tuned model after training. It compares the performance of the 2 models, indicating whether the tuning improved the classification accuracy on the validation set. To summarize, we've covered the foundational concepts of machine learning and deep learning, explored how to build neural network models using Keras and TensorFlow, and discussed the critical steps of evaluating and tuning these models to achieve optimal performance. Deep learning continues to evolve, with advancements in model architectures and training techniques driving innovation across various fields. I encourage you to experiment with building and tuning your own models to harness the full potential of deep learning. Thank you and see you in my next lesson.